flash it to you because in 45 minutes, of course, one can't do justice to explaining equations, but just to give you an idea what kind of complexity and then what is, just to give you the hints, like what kind of mathematics is behind all this. So let me start from the warming up, very beginning, like complexity. What do we mean by complexity? It can appear in various forms. For example, the kind of systems I have in mind are, for example, where complexity arises because of scattering due to disorder in the medium, e.g., for example, disordered systems, Anderson, Hamiltonian, and all these interacting, many body interacting systems. Then it need not be many body interacting systems. The scattering can even appear, the complexity can even appear because of the scattering from a irregular shape boundary of a single particle. Okay, because as many of you might know, that it leads to quantum chaotic dynamics. Then, of course, we all know complexity because of the interaction among particles in many body systems, for example, atoms. Then there are other kind of complexity in classical systems. Like so far, these are the examples I gave you about the quantum systems, but also we have in mind the complexity appearing in classical systems. For example, if you are considering the complicated interference of electromagnetic waves, for example, here this is a plot of 10 monochromatic plane waves interfering with each other, and it can lead to really very beautiful physics, optical vortices and all that, which you probably, some of you have heard Michael Berry talking about it. And then even the signals, for example, right now you are hearing me and you are also hearing many other disturbances in the surroundings in your environment. And all these, the brain is able to decipher all these signals separately. So this is, of course, there is a complicated interactions of signals going on in the brain. So this is, of course, we are talking about these time series analysis here. And again, this is a classical system. As Prashant already said, even the way these stock agents interact with the stock market, or the prices, the falling of the price of petrol can even affect the price of the food you eat at your home. So all these things are quite very complicatedly, in a very complicated fashion, they are all interacting with each other. And of course, it's not only that complexity always leads to some kind of randomness. Actually, even it can lead to coherent patterns emerging out of randomness. But this last topic I will not be included in this business, what I'm addressing today. Okay, so I gave you some glimpse of complexities appearing in the nature all around us. But how does it affect? Why should we conceive? Why should we worry about it? Because of the complexity, physical properties fluctuate from sample to sample, and even in a single sample. And here I'm giving you a number of examples, of course, without getting into detail. For example, here this is the distribution of corona deaths in USA in 2020. This is the second picture is the distribution of TB cases in USA, and the x-axis is the plot and the y-axis is the number of cases. Similarly, here the x-axis is again, I think I can't see it, unfortunately, but I think this is also again the number of days, and this is the number of deaths. And similarly, this is EEG data. This is heart rate fluctuation. And look, these are very classical systems I'm right now showing you. And then you see similar kind of fluctuations you can see in the stock market. Okay, this is a stock market fluctuation. This is another kind of stock market fluctuation. This is a fluctuation in atmospheric data. This is the temperature change in Antarctica. The question is, by looking at these fluctuations, if I don't tell you which picture corresponds to which, can you really differentiate these pictures? All these fluctuations seem to be similar, okay, except they are probably superimposed on different backgrounds, but as far as fluctuations are concerned, they look like same. And actually there is a lot of universality in it. And one way to, and that is what one aspect of today's talk is to address that. Okay, so I have already said how it affects. Due to fluctuations, as I tried to motivate you that there are physical properties fluctuate, all those properties in which we are interested in fluctuate. So for a long time, for 50 or almost 100 years, we kept confining ourselves to knowledge of average behavior of our dynamics, or average behavior of all statistical properties or dynamical properties. But if there are huge fluctuations, and fluctuations are as large as average, then a knowledge of average behavior is no longer sufficient, and you also need to know the fluctuations. So because fluctuations are as large as average behavior, so the other way to say that it's not only sufficient to know the average behavior, you also need to know the distribution of the physical property. Okay, so that means every time you are dealing with a different complex system, you have to reanalyze it, and analysis, the very fact that it is called a complex system, that means it is not easy to analyze it mathematically. So question is, are we really need to look at all these complex systems separately, or the way I showed you pictures that you can't really differentiate between fluctuations of one system from the other, except for the background on which they are superimposed. So that gives you some kind of intuitive hope that is it possible to find a common mathematical formulation for physical properties in a wide range of complex systems, and then you become more ambitious and you say, if possible, single parametric formulation. Okay, so if you have want to study the distribution, you have to look for a physical property whose distribution you can study. But every time you are dealing with a different physical property, you don't want to do the distribution all over again. So the question is, why not look, if you have an operator and if it can be represented in the matrix form, so why not just study the distribution of eigenfunctions and eigenvalues of the generator of that system, and then express all the physical properties in terms of the distributions in terms of the eigenfunctions and eigenvalues. So if you know the distributions of the eigenfunctions and eigenvalues, you can calculate the distribution of the physical property. Okay, so this is the idea. So question is, so far I have not introduced the random matrices. So where is the connection with random matrix come? So basic question is how complexity leads to appearance of random matrices in physical systems. Okay, but before then the question comes, what is a random matrix? So simple, a matrix with random entries, that means entries are no longer well defined. Matrix elements can have some of the matrix elements at least can have some error associated with them, and you cannot exactly determine them. That means they are best described by a distribution. Okay, so now let us first understand how the random matrix can originate in a system. Okay, because whenever we start in our graduate studies or undergraduate studies, we start with harmonic oscillator. So harmonic oscillator, you must have written the harmonic oscillator in various in position basis, in energy basis, and nobody ever talked about any random matrix coming there. So let us see. Let me just remind you. So this is your harmonic oscillator, and this is your eigenvalue equation, and you can n plus half h class omega is the energy level, and n is the eigenfunction in the energy level of this harmonic oscillator. And if you want to calculate the matrix elements of harmonic oscillator in energy basis, okay, you can calculate it will be a diagonal matrix. Similarly, you can write down the matrix elements of Hamiltonian in position basis. Okay, so this is the matrix element in the position basis. But both whether you are studying the Hamiltonian harmonic oscillator in energy basis or in position basis, both of them are well defined. There is nothing random about it. But then comes a question. Now, if you consider two harmonic oscillators interacting via complicated interaction. So let us now look at the two harmonic oscillators interacting. So H1 and H2, two harmonic oscillators, and they are interacting by a potential V12 and H non-interaction. If we put V12 is equal to 0, it is just the summation over these harmonic oscillators, independent harmonic oscillators. So usually, if you want to understand what is the role of interaction in these two systems, then of course, it's best to study the non-interacting basis, write the H in the non-interacting basis. So non-interacting basis, of course, one part corresponds to the first Hamiltonian, other part corresponds to the eigenfunctions of the second Hamiltonian. So N1, N2, and these are the energy levels, non-interacting energy levels. Okay. Now, let us try to write down the Hamiltonian H interacting harmonic oscillator in this non-interacting basis. All of you can do very quickly. This is the formula. And now the question is, if you are considering the diagonal elements, it is very easy to calculate because for simplicity, you can assume that V12 does not contribute to that. And therefore, you have this form for the diagonal matrix elements, but for the for the off diagonal matrix elements, you have this complicated off diagonal matrix element N1, N2 interacting the N1 of first Hamiltonian interacting with the M1 through V12, and N2 of the second Hamiltonian interacting with another eigenfunction of it, M2 through V12. And if you write down it in the integral form, this is the complicated integral you get. And of course, for very simple cases of V12, because you know what is psi N1, what is phi N1 and what is phi N2, you know exactly, because these are the eigenfunctions of the single harmonic oscillator. So you can substitute it here, but whether you can do this integral depends on the form of V12. And if V12 is very complicated, you may not be able to calculate these matrix elements exactly. So then what do? You do some approximation, saddle point approximation, or whatever various kind of approximation techniques you use to calculate this kind of integral, because it's first of all a double integral, and then V12 can be very complicated. So matrix elements of V may not be calculated exactly, especially if you are dealing with very high order energy levels of the harmonic oscillators. Okay, so that means matrix elements are best described by an error, and that what it effectively means that you can describe a matrix element not exactly, but by a distribution. Now, as I introduced the definition of the random matrix already, if some or all matrix elements are random, then H is a random matrix. So H is a random matrix, but in non-interacting basis, because right now you are writing the interacting Hamiltonian in the non-interacting basis. So H is a random matrix in non-interacting basis. Mind you, it need not be a random. It will have a very different form in different bases. For example, in its own eigenfunction basis, it will be a diagonal matrix. So, but let us confine ourselves to this basis only, non-interacting basis. So H will be a random matrix in non-interacting basis. Now, at no point of time I talked about any real disorder in the problem. They were just harmonic oscillators interacting by this potential. There was no disorder. Okay, if you can solve this integral, this potential is well defined. Exactly, formula is given to can be given to you, but still you may not be able to calculate this integral. So there is no disorder, but still a randomness comes into your Hamiltonian matrix, because of your own limitations of calculating this integral. Okay. So H can be a fully or partially random matrix, and depending on what errors you are associate, what kind of matrix elements you are, depending on what kind of matrix elements, the different kind of errors may be associated with different matrix elements. So matrix elements can have different distributions. Okay. So now comes, what about eigenfunction? Okay. So eigenfunctions, if the Hamiltonian cannot be determined exactly, so naturally, if you calculate its eigenfunctions in whatever basis you are studying, eigenfunctions also cannot be calculated exactly. For example, you can write down the eigenfunction of the interacting harmonic oscillator in this non-interacting basis. And that means these two quantities are, of course, well known to you because these are Hermite polynomials, Hermite functions, but you have to determine this coefficient. You know, in quantum information case, in bipartite systems, we always deal with this state matrix. This leads to this Hart ensemble. Okay, so here comes the this is how do you determine these coefficients? These are components of the eigenfunction in non-interacting basis. So how do you determine these components? You have to calculate this overlap, but this overlap need not be calculable exactly because you cannot write down the matrix, even Hamiltonian exactly. So, okay. So even not only the Hamiltonian is random, the randomness of the Hamiltonian manifests itself in the component matrix also, which hereafter I'll refer as C matrix only. Now let us look at another problem. Okay, hydrogen atom. I have deliberately chosen the examples which have been taught to you in your undergraduate course, because this way you will be easily able to connect to what I'm talking. So let us look at the what do you have in a hydrogen atom? One nucleus, one electron, and nucleus and electron are interacting with this kind of Coulomb interaction. Usually we consider the Born-Oppenheimer approximation. That means we neglect the nucleus degree of freedom by saying it is very heavy and therefore it does not move, so we can ignore its dynamics. Then you write down, then you use the effective mass of the electron in this static nucleus picture and solve this problem. All of you have solved this problem. You can write down, these turn out to be spherical harmonics and then exponential decay of the radial direction, in the radial direction, you can write down. However, the question is, nucleus is there and you cannot ignore it, especially the kind of physics nowadays we are doing. You must take into account the nucleus, but nucleus itself consists of many particles. Okay, so what happens if you introduce the nucleus dynamics? Okay, so that means now you have to now not only include this term, instead of this term, you have to include Rn, the position of the nucleus, but position of the nucleus itself is changing because nucleus is also a dynamical, is undergoing dynamics. So it is no longer fixed, and therefore you have to now solve this complicated integral, which is again has a lot of complexity. Okay, and it is not always easy to calculate it. So if you cannot calculate it, again random matrix, the matrix elements are not exactly calculable, and it leads to the Hamiltonian of the hydrogen atom. I mean, it inserts a kind of randomness in the hydrogen atom. Okay, so let me now say, after giving you two examples, now let me say why system-dependent random matrix ensembles. So whatever I have said, I am now repeating. Lack of detailed knowledge about interactions manifests itself by randomization, partial or full of various operators of the system, determination of some or all matrix elements within an uncertainty. Matrix elements are best described by a probability distribution. Uncertainty associated with various matrix elements can be of different types. Matrix elements can have different distributions. So a generator, it need not be Hamiltonian. Even the component matrix, the C matrix, or any classical system, the stock market fluctuations, a covariance matrix will be a random matrix, and some or all, what I define random matrix as, some or all matrix elements are randomly distributed. So if the generator is defined by random matrix, so that means there is no fixed matrix describing your generator. So generator is best described by an ensemble of matrices, each of them equally probable representative of the system. Okay, so what kind of ensemble is this? That depends on the complex system, and obviously depending on the wide range of complex systems we are dealing nowadays in our everyday life or in our all around us, you have to analyze a wide range of random matrices. Okay, so what do you need? We have said, so of course you need to know the distribution of the matrix elements, as I have already have been saying, because if you know the distribution of the matrix elements, from there using this formula, you can calculate distribution of the eigenvalues. Here E1, E2, En are the eigenvalues of the operator H, and rho H is the distribution of the matrix element of H. And if you just do the transformation from the eigenvalues from the matrix space to eigenvalue eigenvector space, and then integrate over all eigenvectors, you can calculate the distribution of eigenvalues. If you know the distribution of eigenvalues, you can calculate all those physical properties which depend on the eigenvalues. For example, partition function, specific heat, and all kind of many other properties I can tell you, like conductance, okay, Landauer conductance and all that you can calculate from the distribution of eigenvalues. Okay, so but to calculate distribution of eigenvalues, first you need to know the distribution of eigenfunctions. Similarly, if you can calculate the distribution of eigenfunctions if you integrate over eigenvalues. And you know, as I will be, if I have time, I will come to that. Distribution of eigenvalues is nowadays very relevant question in context of quantum information. Okay, so comes the question, as I said, physical properties can be determined if you know the distribution of eigenvalues and eigenfunctions, but for that you have to know the distribution of matrix elements. Okay, so how do you determine the matrix elements? Distribution, of course, the most general form can be written by as the joint probability density of all matrix elements subjected to whatever constraints the system is, for example, symmetry, conservation laws, and all that. I'll come to that in more detail. Okay, and I will just tell you now, this looks very complicated. This is useless because you can't do much with it. So, but there is now, we know how to use this. If you have, depending on the constraints on the system, which I'll give you more detail, depending on the, you can often write the matrix element distribution in a Gaussian form, in a multi-parametric Gaussian form, where matrix element HKL is having a mean value BKL and variance VKL. Okay, so this is the ensemble density for a matrix H, Hermitian matrix H, which are Gaussian distributed matrix elements with different variances and different mean values. Of course, if you know the higher order moments, not only mean and variance, then it will lead to non-Gaussian ensembles. Okay, so how did I write this? The question is, I here clearly said that if you have the ensemble constants on the first and the second moment, then you can write down it in the Gaussian form. How do I know that? Actually, there comes to my aid the maximum entropy hypothesis that says that in absence of complete information about the system, the simplest and least biased hypothesis is that the system is described by a distribution that maximizes the Shannon entropy under condition due to whatever information available. And it so happens, like this is the formula for a Shannon entropy. I will not get into more detail. You can read about it in various places. But it so happens that this theorem tells us that if you know, if the information is only available about the first moment and the second moment, it leads to Gaussian distribution. So it's not just like that we keep using Gaussian distribution everywhere. It is quite based on a lot of intuitive ideas. Okay. So as I said, I have been talking about if you know the constraints about the, if you on the first and the second moment, what constraints I'm talking about. Okay. So this is very important aspect because constraints can lead to very different ensembles. So nature of the ensemble depends on global and local constraints based on the physical aspects of the system. They can be of various types. Global constraints are those which affect a matrix directly. That means symmetry and conservation laws. For example, if you have a time reversal symmetry in the system, then the corresponding Hamiltonian can be written as a real symmetric matrix in the time reversal symmetry preserving basis. And of course, the system can have any kind of origin of complexity. It may have disorder or chaos. It may or may not have disorder or chaos. You may not even have randomness. That's what I mean by this last line. But if you use the symmetry preserving basis, the matrix can always be written as a real symmetric matrix. So it has nothing to do with the randomness, presence of it, or lack of it. But now comes that's why I call it matrix constraint, global constraint or matrix constraint. But then comes the ensemble constraint, because that will be based on whether you have randomness, complexity in the system or not. So which affect distribution parameter of the matrix elements. For example, disorder, it can be huge number of constraints. Disorder, dimensionality, boundary conditions, nature of dynamics, interaction among subunits of the system. Okay, So I will call, because sometimes it is not very clear using word global and local. So matrix constraints and ensemble constraints seem to be more a much better phrase. Okay, I've already said global example of global constraints are conservation laws, symmetries, dimensionality, boundary conditions, but dimensionality can also be local constraints. Okay, can also affect the local constraints, means ensemble parameter, that means nature of distribution. So type and strength of disorder, nature of dynamics, interaction among subunits, these are local constraints or ensemble constraints. Okay. Global constraints can lead to different kind of matrices. I will quickly just flash it to you. For example, transfer matrix can lead to non-Hermitian current conservation. In case of transfer matrix, if you have current conservation and time reversal symmetry, it leads to matrix element correlations. Systems with Goldstone symmetry again lead to column matrix elements are correlated to each other by column constraint. Then there are non-Hermitian systems with zero trace, okay, where all energy levels sum to zero, and that also has different kind of constraints. So these are the example of, here I'm talking about a single matrix. I'm not talking about any ensemble. So these are the example of global constraints. Local constraints, of course, affect the nature of distribution. So now let us see how the nature of distribution affects the, how local constraints affect the nature of distribution. So let us take an example of that, the very well-known example, and that will actually connect directly to what I'm going to talk about. Anderson Hamiltonian, it's a simplest model of disordered system, a particle of mass m moving in a random potential VR. Tight binding approximation is the, you write in atomic side basis of the lattice of arbitrary dimension. This is the Hamiltonian in the tight binding approximation. Epsilon k gives you the on-site energies, and VK tells you about how electron can hop from one side to the other. Here K and L refer, K refers to the site and L also refers to another site. Okay. So as I already said, VK gives you the hopping between atomic sites K and L, and you can write in the side basis. It's a simple exercise of the matrix algebra, matrix mechanics, that you can write down that this turns out to the matrix. Okay. In this side basis, K and L. Okay, this turns out to be. So here you see one thing you pay attention, that all the on-site energies are appearing as a diagonal, but hopping is appearing only along the off diagonal, because that is going to be very important. Okay. So how the dimensionality affects the Hamiltonian matrix, because let us look at, I will not talk about all the three cases, but just tell you one simple case because I am running out of time. So if you consider one-dimensional system, that means all sites, all atoms are arranged on along a single line, equally spaced. Okay, so now this red atom, the electron can hop to the next neighbor, nearest neighbor, or the other nearest neighbor. Then what will be the structure of the matrix? Of course, here if you are only talking about the nearest neighbor hopping, that means electron can only hop to here or here, but cannot hop from here to here. So that means these matrix elements have to be zero. If hopping describes the, if hopping is described by the VKL, so that means any, if you now call this 1, 2, 3, 4, so that means 2 and 4, V24 will not be connected. Okay, V24 will be 0, but V23 and V21 will be non-zero. So this is what here, of course, this is here. There is a slight this thing. It should be epsilon 1, epsilon 2, and here these ones are non-zero. That means I've taken hopping as 1, as you can see. So this is a misprint. Okay. Similarly, you can in the two-dimensional case, it becomes a lot more complicated. In one dimension, you saw that the hopping was connecting only nearest neighbors. So you see all these matrix elements are, the next off diagonals are non-zero. Okay. The diagonals are non-zero, and the first off diagonal is non-zero on both the sides. But many other matrix elements are 0. Similarly, you can look at the two-dimensional case and three-dimensional case, and the structure of the matrix is very different in each case depending on what dimensionality you are studying, because two-dimensional allows you to hop not only along the line but also in the perpendicular direction. And in three-dimensional case, there will be two perpendicular directions to hop to nearest neighbor, and naturally the matrix element structure will change. So that's how dimensionality affects. Right now, we are not talking about any ensemble. It is just a single matrix. So that's why in this case, dimensionality is behaving like a global constraint. Okay. But now what happens if the on-site energies are random? Okay. So if on-site energies, still you are considering, but even if they are on-site energies, you allow them to be random. The question is, what kind of randomness? Are this randomness site dependent? Are they independent, or are they correlated? Similarly, you can ask about hopping. Is the hopping nearest neighbor only, or the electron can hop from one end of the lattice to the another, like in a metallic system? Hopping is isotropic or anisotropic. That means on the left side it hops with one rate, and the right side electron hops with a different rate. Or up and down, it has different rates of hopping. Hopping is random, hopping is non-random. So naturally, depending on all these so many possibilities, the matrix elements can be very different, and that's what leads to system dependence of H matrix. That's what I mean by, okay. So, but if you say that even if you consider the simplest case is isotropic hopping, nearest neighbor hopping, and non-random hopping. Okay, so that means, and you can even fix a hopping rate T. So you see all these T are appearing. So hopping is this arrow you see, this is indicating the hopping. Hopping is non-random, isotropic. So that means all the matrix elements are T. If the hopping element amplitude is taken T, so all the off diagonals are either T or 0. Here 0 corresponds to, because you are allowing only nearest neighbor hopping, not far away hopping. Okay. However, if you are allowing on-site energies are randomly distributed, then you see, and as I told you, on-site energies are appearing along the diagonal. So diagonal elements are now randomly distributed. For simplicity, you choose them to be Gaussian, independent Gaussian, not even correlated. So I'm choosing the on-site energies are Gaussian distributed, independent. Okay, immediately it becomes a random matrix. Okay, now the question is, what can you say? Can you calculate the energy level distribution eigenfunctions of this Hamiltonian? Okay, so now this comes the most important part of this. How do you write down you said that I'm taking the diagonal matrix elements as Gaussian distributed. Of course, they are having some mean value epsilon k and some variance hkk. Okay, but you are taking hopping as non-random. So a non-random number is represented by a delta function. Okay, so this is the distribution of a non-random number is a delta function. Okay, so this is what you have. So, but you can still write this delta function as a Gaussian form, because a delta function can be approximated by a Gaussian, and this is, so limit v goes to 0, this function represents a delta function. Okay, in physics we are using this kind of approximation all the time. So basically what I'm trying to say, not only, of course, you have chosen your on-site energies are Gaussian distributed, but now even off diagonals, which were non-random, can also be written as Gaussian limiting Gaussian. Okay, how does it help? Okay, now, but note, they have different, diagonals have different mean values and different variances from the off diagonals. Okay, so as I already motivated Anderson ensemble, I'm just summarizing what I've already said. This is the exact form of the Anderson ensemble with on-site energies, Gaussian distributed, independent Gaussian distributed on-site energies, on nearest neighbor non-random hopping, but this can be written as a Gaussian distribution, multi-parametric. So this becomes that the ensemble density for the Anderson Hamiltonian can be written as a multi-parametric Gaussian ensemble for the case I'm describing. Okay, what can you say about the energy level distribution and eigenfunction distribution of this case? That is the question. Okay, So you see, this system depends on so many parameters. This is Hermitian matrix. We are talking about Hermitian system, and therefore you have to consider only either the diagonals or upper diagonals, because upper half diagonals, because lower half diagonals are same as the upper half diagonal. That's why this summation, this term. And but each matrix element, each diagonal and off diagonal can have different variance and different mean values, the way I told you. Okay, so that means effectively you have to study this system, which depends on at least n plus 1 by 2 parameters. Okay, and it is not a simple system to analyze. So let us see what can we say. So this right now I showed you how it appears in the Anderson system, but I can also motivate you in various other cases, but we don't have time. So let us consider uncorrelated multiparametric Gaussian ensemble. Let us see what can we do about it. What can we do with it? Okay. So again, I'm repeating so that it goes to your, sinks down. Here, this B and V are ensemble parameters. H is the matrix element, and this is describing the distribution of the matrix elements. Ensemble parameters depend on the system parameters. These are ensemble parameters. Ensemble parameters in turn depend on the system parameters, dimensionality, boundary conditions, symmetry conditions, system size, disorder, scattering, and so all system information is contained in the set of ensemble parameters V and B. Different systems will correspond to different ensemble parameters. Okay, but the question is, yes, this can, therefore, this ensemble density or matrix element distribution can take into account, can describe many systems by depending on what are the B values and V values. But the question is, now what I'm going to tell you is, I must say it already, that although you see it depends on so many parameters, ensemble density depends on so many parameters, ensemble parameters, which in turn depend on system parameters. Still, what I'm going to claim is that as far as statistics is concerned, it is described by a single parameter. Okay, and that, of course, in the context of Anderson Hamiltonian, that conjecture was already there, but now I'm going to claim it through analytical means, and also let me see how far can I go. Okay, so first this is just a picture to show you how system parameters, change of system parameters can lead to Anderson ensemble changing from one end to the other. So you see here the color coding is such that the brightest color describes the maximum disorder. Okay, so you see here red color describes maximum disorder, and as you are decreasing the disorder, only the diagonals are changing. Off diagonals you are not changing, hopping rate you are not changing. So those elements which are 0 remain 0. Those elements, the color of all the off diagonals remain same. Only color of the off diagonals, color of the diagonals is changing, and there comes a stage when the color of the diagonal is almost the same as the color of the off diagonal, those which were non-zero. Okay, and when it happens, actually this is the limit when you say ergodic limit or the metallic limit, and this is called the, depending on the hopping, it can be even the insulator limit. Okay, so this is how the transition occurs, metal insulator transition and localization to ergodic transition occurs in the Anderson ensemble pictorially. Okay, the matrix, look, what I want to emphasize, which many people don't know, that the structure of the matrix does not change, only the ratio, the relative strength of the matrix element changes. Those which are zero in every case. But that is not the only route for the localization to ergodic transition. There are many other systems in which there can be a localization to ergodic transition. For example, in quantum chaotic system, in a very different way. But as you increase certain system parameters, it goes slowly and slowly, it picks up all the zero elements, pick up some value, and ultimately they all become same. Okay. So there are various routes to localization to ergodic transition. And okay. So let me, in the remaining time, because now I have only 15 minutes left, and I have a lot of mathematics to show, but you don't get worried. I will just motivate you. You don't have to. I will just indicate the important points. Okay. You don't have to check all the mathematics here. So as I said, we want to study this ensemble density or matrix element distribution, and which depends on so many parameters. Now it can be exactly shown that if you consider the dynamics, why you want to consider the dynamics? Because as I showed that here you are changing the disorder versus hopping ratio, and that leads to transition. So that means you have to consider the changing system conditions. Okay, so if you have to consider, so let us change the system parameters. System parameters change will lead to change of ensemble parameters. And here you consider a change of ensemble parameters in this combination. Here, this is a derivative with respect to VKL. Here I have lost, there should be a row here. There should be a row, I missed it. Yeah, this row. Okay, there should be a row here. So if you consider the first order derivatives of rho with respect to ensemble parameters, it can be written as a diffusion equation in the matrix space. So let me repeat it. Combination of first order parametric ensemble parameter derivatives can be exactly shown as a diffusion in the matrix space. Okay, so the question is, on this side you have lot of ensemble parameters. This side you have no ensemble parameter. So you have often seen a diffusion equation, let's say Fokker-Planck equation of this form. Okay, where time appears on the left-hand side and the right-hand side, you have particle positions appearing. So consider these matrix elements as particles, and here, this is the time-like parameter. The question is, this left-hand side, can it be reduced to a single parameter? Okay, then you have your standard Fokker-Planck equation, which describes the dynamics of particles in a harmonic potential. Okay, and why? Because if we can really reduce this complicated thing to this thing, we already know a lot about the system, and we can use all that information straight away to analyze our y, this definition of y, where y depends on VKL and VKL. GKL is just takes value 1 or 2, depending on k is equal to L or not. K is not equal to L. So you will be able to check if you substitute, if you differentiate using this definition, you will get this kind of left-hand side. You can exactly verify this is an exact definition. Okay, so what I'm trying to say, here you started with the
I think we lost the speaker.
So did you see this slide when I was talking about this?
Yes.
Yes.
Okay. So what I was trying to motivate, because I see I'm already used up my time, 11:44. Okay, so what I was trying to say is that you have, if you know this parameter y, the system information enters only through this. You have to just study this, and y is defined exactly here. So you have to just, so this complicated system can be analyzed by using this different systems. I'm sorry, I've lost my thread actually. Yeah, different systems can be described by equation, and where they will all depend on y, and but y value will be different for different systems because vkl and bkl will be different. Okay, so now how can you calculate from here the eigenvalue distribution and eigenfunction distribution? I'll quickly go through this, because you compare this with the standard Fokker-Planck equation. You can calculate the moments from here, and of course we don't have time. From moments you use because you now will calculate the moments of the matrix elements distribution in terms of the parameter y, and then you use a second order perturbation theory for the eigenvalues. From there you can calculate the moments of the eigenvalues, and once you know the moments of the eigenvalues, now you do the reverse process. Previously you derived the Fokker-Planck equation, and from there you calculated the moments. Now you calculate using the moments of the matrix elements, you calculate the moments of the eigenvalues, and then substitute those moments of the eigenvalues in the standard Fokker-Planck equation, and that leads to the diffusion equation for the eigenvalues. Once you have this diffusion equation of the eigenvalues, you can do all kind of correlations. You can calculate all kind of correlations. Similarly, okay. So, but the beauty of this thing is here, this whole thing is now applicable to many systems, because here system information is entering only through parameter y. So that means, what does it mean? Because any solution will depend only on parameter y, not how y is taking a specific value. Okay, because the formula will only depend on y. So as long as different systems have same value of y, different systems will have same kind of energy level statistics. Okay, now let me quickly go. I don't have time to, because I have used up my time, so I will not give you the, I could have showed you the numerical analysis. For example, here there were 4 different systems. This is the Anderson system, which I've already told you about. This is another matrix, which is all the diagonals have same variance, but all the off diagonals have variance different from the diagonals, but same. I wanted to say something about the eigenfunctions. Okay, so because this is a quantum information meeting, so let me just say. So as I already motivated, randomization of the operator also manifests in eigenfunctions expressed in any physically useful basis. because the eigenfunctions are basis dependent, so you have to talk about basis also whenever you're talking about eigenfunctions. The question is, what about eigenfunction statistics? For example, when you consider in the case of bipartite systems, when you write down any eigenfunction in which whose entanglement you are interested in studying, you write it in the non-interacting basis, product basis, and then you have to consider these component matrix components in the bipartite basis or non-interacting basis, and then the structure of the C matrix, depending on whether you have a separable system, bipartite separable state, or maximally entangled state. The C matrix component matrix can be of different type. Okay, and I could have also showed you the pictures that how the eigenfunctions of different eigenfunctions of various systems. For example, here I have pictures for random field Ising model. The ground state, intermediate state, exercise state, all you can see have different kind of distributions. Okay, so naturally, every time you are dealing with an eigenfunction of even a single system, you have to redo the whole analysis, and you have to first identify what is the component matrix associated with that eigenstate, and then analyze it to calculate its entanglement properties, because first of all, they are going to be random. Okay, so the same procedure can be first or second order perturbation theory can also be extended to this, and you can calculate. I will not talk about it now. So let me come to my conclusion. I have used my time. Sorry for the disturbance. Okay, so what I have tried to say so far, distribution of energy level and eigenfunction correlations of a complex system described by a multi-parametric ensemble of Hermitian matrices with independent element is a non-stationary state of a diffusion governed by the complexity parameter. The complexity parameter is the parameter y, which I introduced, which was a combination of all ensemble parameters, because the parameter y depended on the combination of all ensemble parameters, and therefore I refer it as a complexity parameter. Different systems with because complexity parameter, you have to rescale it if you are studying the fluctuations, and rescaled complexity parameter I call lambda. So different systems with rescaled complexity parameter, although different system conditions, will have same eigenvalue statistics. Okay, and same can be applied to eigenfunction statistics also. These things I have not talked about, so I'll not. Let me now go to the final conclusion. The analysis suggests a possible classification of complex systems modeled by multi-parametric Gaussian ensemble in an infinite range of universality classes, characterized just by complexity parameter and the nature of global physical constraints. That means symmetry and conservation laws, global constraints, unitary symmetries, and confining potential on matrix elements seem to divide complex systems in various universality classes. Each such class can further be divided into a continuum of subclasses characterized by their complexity parameter. So first classification comes from the underlying symmetries and conservation laws. Second, local subclasses depend on the complexity parameter. Okay, let me not get into that. I will just get into the end because I have not discussed in great detail. The formulation suggests a deep-rooted universality. This complexity parameter formulation suggests a deep-rooted universality and a web of connection hidden underneath the word of complex systems. And that's all. I will end here, and you can find the references here. What is this? Just, yeah, these are the references. Thank you very much. I apologize for the disturbance because connection kept breaking down. Thank you very much.
Thank you, ma'am, for this wonderful talk. Now, platform is open for the questions. So anybody wants to ask, so they can unmute themselves. Go ahead.
So I have one question. Thank you for your talk. So this is a for my clarification. We may lose very delicate quantum effects such as interference by introducing random matrices or distributions. So my question is, did you study impact on quantum interference by introducing random matrix?
See, the thing is, it's not the question that you are introducing random matrix. You, as try to motivate you, you have no option. It's not that you're trying to use it as a tool. This automatically comes because of your own lack of calculation ability. I mean, your means humanity. We cannot calculate beyond. The existing formulations just give you to a certain limit. You will use saddle point approximation on this. Look, almost any basis you calculate your eigenfunctions. Quantum, for example, you are talking about quantum interference. Of course, you have in mind waves, and now waves are traveling in some space. And whatever, if you try to study the interference and you have some basis, and you try to write down this interaction matrix, you will not be able to calculate, especially the moment complexity increases. So first of all, you cannot. The idea is, even although you have limitations to calculate your matrix elements exactly, although there is no randomness in the system, but with even that kind of limitation, how best to extract the information and exact information which actually works. That's so. It's just because I tell you. So to come back to your question, when you said there can be very small, very minute details of the interference which we might miss out in randomization. Okay, so the answer is the existing evidence suggests us those minute details do not really matter, because otherwise you will not see this kind of universality which has been seen from the smallest system, an electron moving inside a lattice, to the stock market fluctuation, to the dynamics occurring at a planetary scale or the universe scale. Okay, so irrespective of what kind of time scales or energy scales or length scales you are associated, as long as there is a complexity, dynamics. For example, you see one kind of random matrix is just explaining the behavior of the system. Okay, so that tells us whether the complexity is arising from the stock market or complexity is arising because of the electron getting affected by phonons or existing atoms. It does not matter. So okay, so the third part of the question, whether I have studied, I have not studied quantum interference. By quantum interference, if all the time we are studying the eigenfunctions, and when you talk about we are studying quantum correlations, quantum interference is also a kind of correlation, and quantum interference is also a study of quantum correlations basically. So in that sense, of course, I have studied, and I'm studying like entanglement, but I don't know exactly which kind of study you have in mind. But to answer in one line, if possible, you do it exactly, but it is not possible. And that's why you have to, randomness comes in because of your own limitation, you can't avoid it. Hope I have answered your question.
Yeah, thank you.
Yes.
We still have a 1 minute. If anyone want to ask questions, still can ask.
I can comment on the yes, which you asked whether I have some picture in my mind regarding quantum interference. Yes, I have. Sure, I will share with you very delicate effects, quantum QIQT states. So if there is no interference between two macroscopic states, then we will see only two Gaussian distributions.
Oh, I see now what, you are talking about very subtle correlations, right?
Yeah.
So right, very subtle correlation. Yeah, the thing is, yeah, so that's why the whole idea about the system-dependent matrix ensemble is not talking about, look, for ergodic systems, random matrix theory works has been known now for 50 years. I'm not this system dependent, like when you are taking into account those very minute details. As I said, that I showed you a matrix in which all matrix elements, all off diagonals were non-random. Only diagonals were random. So it's like this. So you're talking about now quantum cat states, and you are saying, so correlations. So here you will calculate the matrix elements. Now, if you can calculate it exactly, well and good, you study. If you cannot calculate it exactly, then there will be some kind of error associated with those matrix elements. And you have to take that into account and see whether that error matters.
It is clear.
See,
Thank you.
You are assuming that those subtle correlations are going to really affect. Yeah, they can affect, but their effect can manifest in a very different way than you can presume. Of course, you have to study. I mean, like that. Again, I'm repeating myself that if you can study exactly, you study it exactly like harmonic oscillator. And then I suggest you do another thing. Now, the elements which you cannot calculate exactly, you allow them some kind of randomness and see whether the result really changes. Whether you really have any different result, drastically different result, or what is the effect of, you are talking about two cat states interacting, fine. Now you are again assuming that these two cat states, you know all the details. First of all, cat state itself is a modeling of your system. And then you are assuming, so that model itself includes some kind of approximation. And then you're assuming you know all the interactions details. I'm saying you don't know. And you assume whatever detail you think you know, you go ahead and do the exact analysis and later on allow some kind of randomness and compare the two results and see whether the results are different. I doubt it will be different. You will not see drastic difference depending on the okay. So I think there are no more questions, so we can stop.
Yes, thank you, ma'am, for this wonderful talk. Now we will move for our next speaker.